Alright, here we go, last video. So this is going to be 10 through 13. 10 is the last of the multiple choices, and it is a bit of a doozy. There's nothing like this on the test, and I'll try to explain this one as best I can, because I don't really think we had one like this really in the class at all. So this is talking about the lean body mass and metabolic rate for 5 adults, which is a very small sample, and for each person the lean body mass is the subject's total weight in kilograms less any weight due to fat. The metabolic rate is the number of calories burned in a 24-hour period. So I've got their lean body mass and their calories burned. And it says because a person with no lean body mass should burn no calories, it makes sense to model the relationship of the direct variation function in the form of y equals kx, where in this case k is going to be the slope for this situation. And the reason there's no y-intercept here is because the y-intercept would be 0, is basically what they're saying. The models were tried using different values of k, 25 and 26, etc. And the sum of the squared residuals was calculated for each of the values of k. Here is the scatter plot showing the relationship between the SSR, which is the sum of the squared residuals, and k. So we've got this parabolic looking thing here, and it looks like the book that I chose must have had a sleeper in class at some point, because this kind of looks like maybe somebody was drooling on my book, perhaps, and somebody made a little mark right here. And according to the scatter plot, what is the ideal value of k for use for predicting the metabolic rate? Well, the ideal value of k in this case is going to be 31, because that is your lowest point in this sort of parabolic. It's kind of the vertex in this parabolic shape. So it has the, for lack of a better way of saying it, I guess, it has the lowest value of the squared residuals in this case. So 31's it. I don't think you're going to see anything like that on the test. Lord, I hope not anyway. That's a nightmare. I would try not to be that mean. Maybe a little mean, but not that mean. Okay. Number 11. We've got to get the data in our calculator. I've done that here with L1 and L2. And at first it says make a scatter plot of the data using the explanatory variable and describe what I see. So making that scatter plot, I'm going to go to my scatter plot, so second y equals. Make sure my plot is on. Make sure my x list and my y list are correct. They are. And I'm going to graph that guy, and if I don't see it, I'm going to go zoom 9. And I have a pretty linear pattern there. So that's really what I'm going to say is I see a strong, what appears to be a strong linear pattern with very little variation in that pattern. Now it says find the equation of the least squares regression line. I'm going to do that in the calculator as well. So maybe a quick sketch on that would be great. What I do want, though, if you sketch that, or when you sketch this stuff, is to make sure you label your x and your y axes. You don't have to put the numbers down so much as what is the x and what is the y. And in this case, the x is her age and the y is her height. Okay, so if I'm calculating that least squares regression line, I'm going to go back to stat, calc, line reg a plus bx, where a is the y-intercept and b is the slope. Get my L1 and my L2 back in there. And I can store the regression equation. I don't know that I have to or not, but that shortcut is alpha trace. Choose maybe y1. Calculate. Why not while I'm here, right? Okay, so my y-intercept is about 72, and my slope is about 0.38. R squared, 0.988, and R is 0.994, very strong linear in there. Let's see, and what does that say? Find the equation of the least squares regression line. That equation would be, oh man, where did my sticky go? Here we go. That equation would be y hat equals 71.95 plus 0.38, that's fine, x. Got that? Good. Gone. Okay. Calculate and interpret the residual for the point when Sarah was 48 months old. Oops, I just hit graph. Let's see if I can use this. So I'm going to try calculating a value of 48. So it gives me a y value of 0.95. So what I did on that is I went second trace for calc, and I put in a value for x. I put in 48. I haven't shown you that yet, but that's kind of a slick trick. But you can also just plug it into your equation here. So I've got 90.35 for the y value. So our residual is going to be 90.35, the calculated, minus the y hat value, which is 90 right here, which equals 0.35. There's my residual. So it's pretty close. That goes in line with my y hat, my regression being strong. And would we be confident in using the equation from part B to predict Sarah's height when she is 40 years old? Absolutely not. Main reason being that, well, Sarah's not going to grow until she's 40. In fact, she's probably going to slow down at about 15, and her graph is going to do something like this. In fact, as she ages, she'll probably even shrink a little bit. Oh, you can't see that. Sorry. There we go. So, youth growth, peter off your adult, and then in your older adult years, you're going to drop down. So, this would be a massive extrapolation, and she'd probably be 10 feet tall if you did that. So, no, by no means should she do that. All right. Number 12, drilling down beneath a lake in Alaska yields chemical evidence of past changes in climate. Biological silicon left by the skeletons of single-celled creatures called diatoms is a measure of the abundance of life in the lake. A rather complex variable based on the ratio of certain isotopes relative to ocean water gives an indirect measurement of moisture, mostly from snow. As we drill down, we look farther into the past. So we have a scatter plot from 2,300 to 12,000 years ago. Identify the unusual point in the scatter plot and estimate its x and y coordinates is A. So this guy right here is going to be our unusual point. It looks like the x is maybe negative 19.5 maybe. And its y is just under 350, maybe 340. So if I were estimating that for A, I'd say, what did I say, negative 19, actually, what am I doing? I'm going the wrong way. About negative 19.3, perhaps, and about 340 for the y. Okay. Describe the effect the point has on I, correlation. So what is this doing for the overall grouping? It's actually making that weaker, right? So my R value, my correlation for I, R will be weaker. And the reason for that is this point is stepping outside of our expected line area. It looks like everything else is within a reasonable distance, but this one's just not. You could certainly expand on that. R will be weaker. So R will be maybe a better thing is going to be closer to 0. I guess I need an L in there. Closer to 0. Blame it on Sunday. I can't write. My pen or my pencil's a little weak. All right. Double I. One of these days somebody's going to turn in their assignment on sticky notes. The slope and y-intercept of the least squares regression line. So what is happening to the slope and the y-intercept? Well, what's happening is it looks to me like this line would come through about like so naturally. So this point is dragging the slope to become more flat. So it's actually becoming a smaller negative, if you will, closer to 0. So it's decreasing the slope. And it is also, if you kind of look at what my pencil's doing here, this y-intercept is not exactly right. I mean, there's a big gap between where we're at and where we would be. Like 0 isn't there. But you can see that that would also decrease the y-intercept by kind of almost a pendulum kind of fulcrum kind of effect here. Maybe it fulcrums about here to do that. So the the y-intercept will decrease. And the slope, the negative slope, will decrease. Meaning it'll become closer to 0. It's flattening out a little bit. All right, and the standard deviation of the residuals. It is increasing the standard deviation of the residuals. If you could imagine standard deviation being some distance across here. Don't draw in your book. This is bad, but it's already been slobbered in, so it's okay, right? So your standard deviation is going to be your typical distance away from the line of regression, and this is not anywhere near a typical distance, so it is going to actually increase by being there. It's going to increase that typical distance. So the standard deviation, or the typical distance from the line, is increased. Okay, bad teacher. I'm going to erase my work. There we go. All right, and 13. Long-term records from the Serengeti National Park in Tanzania show interesting ecological relationships. When wildebeest are more abundant, they graze grass more heavily, so there are fewer fires and more trees grow. Lions feed more successfully when there are more trees, so the lion population increases. Researchers collected data on one part of this cycle, wildebeest abundance in thousands of animals, and the percent of grass area burned in the same year. The result of the least squares regression of the data are shown here. So here we have our scatter plot. It appears to have maybe a moderate weak pattern. It's certainly, I don't know that I'd call that strong, but it's certainly got a negative pattern there. This is the residual plot, and I don't see any particular pattern in there. We actually want to look, we want to see no pattern, and we don't really want to like make a pattern in something that sort of has no pattern. So a reasonably patternless residual graph. Here we've got our data. So I've got the y-intercept and the slope, and I've got S for standard deviation, and R squared. So the R squared value is greater than 0.5. So between the residual plot and the R squared value, I think we can reasonably say that this is a linear model, works. So A, is a linear model appropriate for describing the relationship between wildebeest abundance and percent of grass area burned? I would say yes, because we have a scattering in our residual plot and our R squared is greater than 0.5. Question: is R negative or positive? And the answer to that would be it is negative because the slope is negative. I went over that in a previous problem. Give the equation for the least squares regression line. Be sure to define any variables you see or use. I guess I'm not seeing the variables here. So my least squares regression line, this is for B, is going to be y hat equals 92.29 minus 0.05762x, where x is wildebeests in thousands, and y hat is percent burned. Okay. All right, interpret the slope. Does the value of the y-intercept have meaning in this context? It sounds like there's two questions there. If so, interpret the y-intercept. If not, explain why. So that's more than one question. I'm going to say that the slope, we're talking percents here of area burned. So for every 1,000 wildebeest, extra wildebeest in the population, we can expect a decrease of about 6% of the burned area, a decrease in burned area. So about a 6% decrease for every 1,000 wildebeest. That's our slope. The y-intercept has no meaning here simply because it would be an extrapolation to imagine zero wildebeest being that there not being a wildebeest population, and it would be sort of silly to imagine interpreting any kind of relationship there. So it's, like I said, it's an interpretation problem. I think how you would interpret that, if it did make sense, is that about 92% of the Serengeti is going to burn if there are no wildebeest, but that doesn't really make sense in this context. And interpret the standard deviation of the residuals and R squared. That's actually S right there. So interpreting that, we would say something along the lines of we expect about 16% variation between what's actually burned, typically what's actually burned, and what we predict. So plus or minus basically about 16%. And R squared is going to be about 64.6% of the variability in percentage of area burned is accounted for by the least squares regression line with X number of wildebeest per 1,000. So I've said that sort of indicates your level of goodness of prediction, and so we've got it's not bad. It's not bad. All right, guys, I hope you have a good time on the test. I hope it's a real fun time for you. I think these questions are far harder than basically what I have for you. So if you can get through these and kind of make sense of these, I think you'll be all right. We're also testing on Chapter 2, which we went through a number of those questions. I'm not going to do that again, but we went through a number of those questions in class. So anyway, hope you had a great weekend, and I'll see you Tuesday.